All right, we're going to start off by looking at all things factoring. We've got four different techniques that we're going to look at, one being the greatest common factor, then factoring trinomials, either a equal 1, a does not equal 1. We'll look at difference of squares and the sum and difference of cubes. So let's start off here factoring the greatest common factor. Now, for our GCF, if we're just taking a look at any sort of GCF problem, let's take a look maybe at 9x to the fifth minus 18x squared. So we're going to take a look and make sure that we're checking out this numbers first. So for my greatest common factor, I want to check 9 and 18. Well, I know that 9's factors are 1 times 9 and 3 times 3. I also know that 18's factors are 1 times 18, 2 times 9, and we could kind of stop there because we can see that 9 goes into both. So 9 would be the largest number that goes out. X to the fifth and x squared. We always look at the lower power, and if we see x squared, we can see that is the biggest thing that I can take out. Now, that is my GCF. What I do next is I take and divide that GCF into both terms. So 9 divided by 9 is 1. This is a part of my leftovers. And so that would be 1. X to the fifth divided by x squared is x cubed. We take 2 away from the power using the exponent rules. Now 18 divided by 9, we should know that that is 2, and the x squareds go away, leaving me with 9x squared as my GCF, and then x cubed minus 2. This would be our factored form that we would be looking at. All right. Let's take a look at an example dealing with factoring trinomials. Now, there are two cases in trinomials. There's a case 1 where a equals 1, and a case 2 where a does not equal 1. So anything other than that. And when I refer to a, we're talking about a general form of a quadratic, ax squared plus bx plus c. Okay? So when we are looking at a factoring problem, let's take a look first at say just a equal to 1. So something, let's take a look at case 1, where we have x squared plus 7x plus 10. Now, in a situation like this, a lot of times we will do the x factor. That's a more common technique that we have. And we'll take this number here and plug it in up top of that x, and this number down here we'll plug out below. And we'll say, what two numbers will multiply to get 10, but add to get 7? So we're really looking at the factors of 10. And the factors of 10 include 1 times 10 and 2 times 5. That's pretty simple there. We know that 1 plus 10 is 11, so that doesn't work, but 2 plus 5 is 7. So 2 and 5. And so we would get x plus 2 and then x plus 5. We can just kind of drop those down low. That would be a good case 1 situation. So now we need to take a look at case 2. In case 2, this is where a does not equal 1. And in a case where a does not equal 1, something like 5x squared plus 17x plus 14 seems to be a good situation here. So what I would do in this instance, you can start with the x factor again, but a lot of times we don't like this number in front, so we will multiply this kind of 5 times 14. And when we do a multiplication of 5 times 14, what we will see here, that's going to give me the number I'm trying to multiply to from before. So 5 times 14 is, let's see, 20, and so 70. And then 17 is going to be the number we add. So we still kind of pull this number down here. So we're looking at our factors of 70. That must probably give me 70, but add to get 17. Well, that's going to be 10 and 7. 10 times 7 is 70. 10 plus 7 is 17. So here's how I rewrite it. 5x squared plus 10x plus 7x plus 14. And what we just did was we split that 17x. Nothing here we wrote down is not true. So from here, I go to the technique of grouping, and I say, what is my GCF of 5x squared and 10x? That would be a 5x. And then I'm left with x plus 2. What is my GCF of 7x and 14? That is a 7, leaving me again with x plus 2. You should notice that these two things are the same. If you did it right, they should be. And we regroup, leaving me with 5x plus 7 and x plus 2. That would be our final factored form in a case 2 scenario. Still using the x factor in that. We've got two more factor techniques to take a look at, and one of them is super quick. This is the difference of squares, also abbreviated as DOS. So really, one example here, we'll just take, let's say, 49x squared minus 100. Now, no matter what, you should always try to do the greatest common factor, but 49 and 100 do not share anything. So what we'll do is we'll notice that there are two terms, 1, 2. They are both perfect squares, since it's a difference of squares. And there is a minus sign between them for difference. So we're going to take the square root of 49x squared. And we're going to take the square root of 100. The square root of 49x squared is 7x. The square root of 100 is 10. And then we can now do our factor technique and just say that that is 7x plus 10 and 7x minus 10. In fact, every difference of square is this form, a squared minus b squared, that when broken down becomes a plus b, a minus b. So we could try it again with any other difference of squares. We could say x to the power of 4 minus 36. So in this case, we take the square root of x to the 4th, which we divide the power by 2, giving me x squared. We'll take the square root of 36, which is 6. So in this instance, it would all be equal to x squared plus 6, x squared minus 6. Now, technically, you could probably rewrite this as the square roots of 6, but we don't need to go that far. We can leave it just so for now. This now takes us to our last form, which is the sum and difference of cubes. So this one is very similar to what we just did in difference of squares, but in this case, we have two situations. It's not just the difference of cubes. So it's sum and difference of cubes. Let's take a look at this one to start. So we have a root, which is a cubed minus b cubed equals a minus b, then a squared plus ab plus b squared. Now that's one scenario. The other scenario, since this would be difference, would be if I took a cubed and I added b cubed to it. So in that case, we would have same sign, a plus b, then a squared, opposite sign, and then always positive. So what I was just saying there is called SOAP. Same, opposite, always positive. So let's take a look at a difference of cubes and see how SOAP helps me with this. I'm going to say 125 minus v cubed. So this is a difference of cubes. We can take the cube root of 125 and the cube root of v cubed. So this will become 5, and this will become v. Now I know a and b. So when I try to write the factored form of this, I'll go here. Oh, a is 5. Same sign as the minus, so minus v. Let's take 5 and square it, making 25. Opposite from SOAP is going to give me plus 5 times v. 5v, always positive on b squared, and that's going to be plus v squared. This would be a difference of cubes situation. Let's take a look then at a sum of cubes and how SOAP also works in this. So let's keep this relatively simple here. Let's say that's situation 1, here's situation 2, x cubed plus 8. So in x cubed plus 8, we're going to take the cube root of x cubed, which is x. We're going to take the cube root of 8, which is 2. 2 times 2 times 2, that's 3 times is 8. And now we're going to rewrite this. So a is x, b is 2. Now, same sign, it was a plus, so there you go, same sign. X, we'll square it, opposite sign here, so this was 2 minus, right, 2x, so we multiply a and b. And then we have always positive here at the end, so we're going to do plus, and then 2 squared is, so this would be the factored form of x cubed plus 8. We would then see if I could say, try to factor this trinomial. We cannot. So we'll leave it just so. That would be its fully factored form.